Tonight, we're going to try to answer one of the oldest questions ever asked. Does space end? And if it does, what's on the other side? If it doesn't, what does it even mean for something to go on forever? This isn't just a question about distance or astronomy. It's a question that cuts right to the edge of what science can actually tell us and what it might never be able to. Because the further you push into this, the more you realize the universe isn't just big. It's built in a way that makes the question almost impossible to answer, and the reasons why are stranger than anything you've imagined. By the end of tonight, you're going to understand not just what the universe is, but what it means to live inside something that may have no edge, no boundary, and no outside at all. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Stand outside on the darkest night you can find, far from any city, and look up. You can see roughly 5,000 stars with your naked eye. 5,000 points of light spread across the dome of the sky, and every single one of them is close, cosmically speaking. The farthest star visible to the naked eye is about 16,000 light-years away. That sounds large, but the Milky Way alone is 100,000 light-years across. We're barely looking past our own neighborhood and beyond the Milky Way. There's the Andromeda galaxy, 2.5 million light-years out, a faint smear of light on a dark enough night. Beyond that, 2 trillion more galaxies, some of them so distant that the light reaching our telescopes left them nearly 14 billion years ago, when the universe itself was barely recognizable. The first instinct, when you hear numbers like these, is to just keep scaling up, to imagine bigger boxes and more galaxies inside them. But that instinct leads you exactly wrong, because the universe isn't a bigger box. And the question of where it ends isn't a question about running out of galaxies. It's a question about the geometry of space itself. And that geometry is one of the most bizarre and counterintuitive things physics has ever uncovered. The universe, as best we can measure it, had a beginning, roughly 13.8 billion years ago. Everything that exists, all the matter, all the energy, all the space, all the time, emerged from an extraordinarily hot and dense state. This is what we call the Big Bang, not an explosion in empty space. There was no empty space before it. Space itself was created in that event, or more precisely, the framework of space-time that everything exists within came into being. Whatever came before, if that word even applies, is not something physics can currently reach. In the first fractions of a second after the Big Bang, the universe was unimaginably small and hot. Temperatures of tens of millions of millions of millions of millions of degrees. All the matter that would eventually become galaxies, stars, planets, and you, compressed into a volume smaller than the smallest thing you can imagine. Then it expanded, not into existing space. Space itself expanded, every point moving away from every other point, not because things were flying outward through emptiness, but because the emptiness between them was growing. This distinction matters enormously, and we'll come back to it. Within the first 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to stick together and form the first atomic nuclei. Hydrogen, helium, trace amounts of lithium. That's it. The entire periodic table of elements beyond those three would have to wait hundreds of millions of years for the first stars to form and burn and collapse. For the next roughly 380,000 years, the universe was too hot and dense for electrons to settle into stable orbits around those nuclei. It was a fog, an opaque plasma of charged particles through which light could not travel freely. Then the universe cooled enough for electrons and nuclei to combine. The fog lifted. Light traveled freely for the first time. And that first light is still traveling today. It's called the cosmic microwave background, and it represents the oldest radiation we can detect. A glow from the very moment the universe became transparent. We can map it across the entire sky with extraordinary precision. And what it tells us about the early universe is among the most important data in all of science. The cosmic microwave background isn't just a historical curiosity. It's a diagnostic tool. By studying the tiny temperature fluctuations in that ancient radiation, cosmologists can determine the age of the universe, its composition, its rate of expansion, and most relevant to our question tonight, its geometry. Is space flat? Positively curved like the surface of a sphere, negatively curved like a saddle? These aren't abstract questions. The curvature of space determines whether the universe is finite or infinite, whether it loops back on itself or extends without end. General relativity, Einstein's theory of gravity, describes how mass and energy curve the fabric of space-time. The overall curvature of the universe depends on how much mass and energy it contains relative to a critical density. If the actual density equals the critical density exactly, space is flat. Euclidean geometry applies on the largest scales. Parallel lines stay parallel forever. If density exceeds the critical value, space curves positively and the universe is finite, though possibly enormous and without any edge. If density falls below it, space curves negatively and the universe is infinite. Measurements from the Planck satellite, which produced the most detailed map of the cosmic microwave background ever made, found that the universe is flat to within an uncertainty of about 0.5% flat, or so close to flat that any curvature is below our ability to detect. What does that mean for the question of whether space ends? It means the universe is almost certainly either infinite or so incomprehensibly large that the difference between infinite and enormous doesn't matter for any practical purpose. But it doesn't mean there's no limit to what we can see. Here is the critical distinction that most people miss when they first try to think about this problem. There are two different things you might mean when you ask whether space ends. You might mean, is there a boundary to the actual universe? Or you might mean, is there a limit to what we can observe? These are completely different questions with completely different answers. The observable universe has a very definite edge. Not because space stops there, but because light has a finite speed and the universe has a finite age. Light travels at roughly 299,792 kilometers per second in a vacuum. Fast, but not instantaneous. The universe is 13.8 billion years old. That means the farthest any light can have traveled to reach us is 13.8 billion light years. Any object beyond that distance could not have sent us a signal yet. The signal hasn't had time to arrive. This boundary, the farthest distance from which light could possibly have reached us, is called the cosmological horizon, or the particle horizon, and it sits at about 46 billion light years, not 13.8. Because space has been expanding during all the time that light was traveling. The galaxy whose light we're just now seeing for the first time, the galaxy that emitted that light roughly 13.8 billion years ago, is now, in the present moment, about 46 billion light-years away from us. Space stretched between us and it during the journey. So we live inside a sphere with a radius of approximately 46 billion light-years. And within that sphere, we can potentially observe things. Roughly 2 trillion galaxies. Some estimates suggest even more. Outside that sphere, space presumably continues. We just can't see it. Not because there's nothing there, because there hasn't been enough time for its light to reach us. This is already strange enough, but the strangeness gets considerably worse. The expansion of the universe is not slowing down. It's accelerating. In 1998, 2 independent research teams studying distant supernovae expected to measure how gravity was gradually slowing the expansion. What they found instead was the opposite. Distant galaxies weren't decelerating. They were receding faster and faster. The universe's expansion was speeding up. This was such a shocking result that the researchers spent considerable time checking their data before publishing. Saul Perlmutter, Brian Schmidt, and Adam Rees eventually shared the Nobel Prize in Physics in 2011 for this discovery. The cause of accelerating expansion is attributed to something called dark energy, an energy embedded in space itself, pressing outward against gravity. We don't know what dark energy is at a fundamental level. We know it exists because we can measure its effects. We know it makes up approximately 68% of the total energy content of the universe. And we know it means something deeply unsettling for the future of our observable universe. As expansion accelerates, distant galaxies recede from us faster and faster. Eventually, the most distant ones will be receding faster than light can travel through space. Not because anything is moving through space faster than light. Nothing does. But because the space between us and them is growing so rapidly that light emitted toward us today from those distant galaxies will never reach us. The expansion will carry the destination away faster than the signal can travel. When that happens, those galaxies vanish from our observable universe forever. They cross what's called the Hubble horizon, the boundary beyond which objects are receding from us faster than light. Today, the Hubble horizon sits at about 14 billion light-years. Galaxies beyond that distance are already receding faster than light. We can still see them because we're seeing light they emitted in the past, when they were closer to us. But any light they emit today will never reach us. They are, in a meaningful sense, already permanently cut off. And the Hubble horizon isn't static. As acceleration continues, it shifts, and more galaxies fall permanently out of our reach. In tens of billions of years, the only galaxy cluster visible from any location in the universe will be the immediate local group. Future astronomers will look out at an empty sky and have almost no way of knowing there was ever a larger cosmos. All the evidence will be gone. Not because anything was destroyed, because physics erased the view. But this is all about what we can see, not about what exists. The actual universe, beyond the observable boundary, presumably continues. And here, the question becomes genuinely difficult. Does it continue forever? Or does it eventually end? There are 3 broad possibilities, and none of them is particularly comfortable. The first possibility is that the universe is truly infinite, flat, boundless, extending in all directions without limit. No edge, no boundary, no outside. If the universe is infinite, then space doesn't end anywhere. You could travel in any direction for any duration and never reach a wall, a fence, a final galaxy, a last photon of light. There would simply always be more. More space, more matter, more galaxies, more everything. An infinite universe is philosophically challenging because we've never observed anything that is genuinely infinite. Our telescopes don't see forever. Our instruments have limits. Everything we measure is finite. But infinity is not physically impossible just because we haven't observed it. And current data is fully consistent with the universe being infinite. In fact, a flat, infinite universe is arguably the simplest interpretation of what we measure. The second possibility is that the universe is finite but unbounded. This sounds like a paradox, but it's actually the simplest concept to understand if you start with a familiar analogy. The surface of a sphere is finite. You can compute its area. It covers a definite amount of space, but it has no edge, no boundary. If you walk in a straight line on the surface of a sphere, you eventually return to where you started. You never hit a wall. The surface curves back on itself. A finite but unbounded universe works similarly, just in 3 dimensions of space rather than 2 dimensions of surface. If you traveled in a straight line far enough, you would eventually return to your starting point. Not because you turned around, not because space ended, but because the geometry of space curves back on itself. The universe would be like the interior of a 4-dimensional sphere, a closed universe. For this to be the case, the universe would need to have positive curvature. And current measurements suggest it's very close to flat, not positively curved. So while this is a theoretical possibility, the data doesn't particularly favor it. Unless the observable patch we can see is so small compared to the total universe that we're seeing only a flat-looking piece of a curved whole, which, it turns out, can't be ruled out. The third possibility involves the most exotic physics of all. The universe might have a non-trivial topology. You can have a flat space that nevertheless connects back on itself through identifications or structures we don't yet have evidence for. In these models, you could travel in a straight line and return to your starting point even without positive curvature. Think of a video game where you walk off the right edge of the screen and reappear on the left. The geometry of that game world isn't curved. The surface is flat. But the topology causes it to connect back on itself. A universe with non-trivial topology could work the same way. You'd travel in a straight line, and after enough distance, you'd find yourself back where you started. The universe would be finite, but would look flat locally. Some cosmologists have searched the cosmic microwave background for signatures of a small universe with such topology. Patterns that would repeat. Circles in the temperature map that match across opposite regions of the sky. The signature you'd expect if 2 opposite parts of the sky were actually looking in opposite directions at the same distant wall of the universe. So far, no convincing signal has been found, which pushes the topology scale, if it exists, beyond the observable universe, leaving us, again, with no ability to resolve it. The honest answer to where the universe ends is that we don't know. What we know is the observable universe. What lies beyond it is, by definition, not something we can currently measure. But there is one framework that makes the question even more interesting. Possibly, the most important piece of the cosmological puzzle is a theory called inflation. Inflation is the idea that in the very first fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid expansion. Not the gentle Hubble expansion we observe today. Something vastly faster. The universe doubled in size, again and again and again, in a tiny sliver of time. By how much? A region the size of a proton expanded to at least a cubic meter in roughly 10 to the power of -32 seconds. Some models have it expanding far more than that. Inflation was first proposed in the early 1980s by Alan Guth, who was trying to explain several puzzling features of the early universe. The horizon problem. Why is the cosmic microwave background so uniform in temperature across regions of the sky that should never have been in contact with each other? If the universe had been expanding at the normal rate since the beginning, distant regions of the sky would never have had time to exchange heat and reach the same temperature. And yet they are, overwhelmingly, at the same temperature, different by only 1 part in 100,000. The flatness problem. Why is the universe so precisely close to critical density? General relativity tells us that small deviations from flatness in the early universe would have grown dramatically over time. A tiny excess of matter density in the early universe would have caused it to collapse long ago. A tiny deficit would have caused it to expand so fast that no structure could form. The fact that the universe is still so close to flat billions of years later requires extraordinary fine-tuning at the beginning. Unless inflation happened. Inflation solves both problems elegantly. A tiny region of space, originally small enough to be in thermal equilibrium, inflates to encompass everything we observe. That's why the temperature of the cosmic microwave background is so uniform. It all came from one small connected region that had time to reach the same temperature before inflation stretched it to cosmic size. And inflation naturally drives the geometry toward flatness. Whatever initial curvature existed, inflation stretched it away, like drawing a dot on the surface of a balloon and inflating the balloon enormously. The dot doesn't change. But the curvature of the surface underneath it becomes effectively unmeasurable. Any small region, any observer in that region, sees a flat local geometry. The observational predictions of inflation match what we see. The pattern of temperature fluctuations in the cosmic microwave background is precisely the pattern you'd expect if inflation occurred. The slight variations in density that seeded the formation of galaxies are consistent with quantum fluctuations stretched to cosmic size during inflation. Quantum uncertainty, operating at subatomic scales in the earliest moments, became the seeds of galaxy clusters spanning hundreds of millions of light-years. Most cosmologists accept inflation, or some version of it, as part of the standard picture. But inflation comes with a consequence that is, to put it mildly, vertiginous. If inflation can happen once, in one region, it can happen again, in other regions. And this is the theory of eternal inflation. In eternal inflation, the inflationary process never truly stops. It continues in most of space. In some regions, inflation ends, the inflaton field decays, and a hot, dense universe like ours is born. In other regions, inflation keeps going. And in still others, inflation ends but produces a universe with different physical constants, different laws of physics, different particle masses, different values for the fundamental forces. The outcome, in its most complete form, is that there are infinitely many universe-sized regions, each a bubble where inflation ended, each potentially different from all the others. This collection of bubble universes is called the multiverse. Not in the science fiction sense. Not parallel dimensions, where different versions of you made different choices. But vast, causally disconnected regions of spacetime, each of which evolves separately and may operate under entirely different physics. Some bubble universes might have a different value for the fine structure constant, the number that governs how strongly charged particles interact with each other. Even a small change to that number would make atoms impossible, or stars, or chemistry of any kind. Some bubble universes might have more or fewer spatial dimensions. The mathematics of string theory, which is one of the main theoretical frameworks that produces eternal inflation, admits solutions with anywhere from 4 to 10 or 11 spacetime dimensions. Universes with more spatial dimensions would behave in radically different ways. Some bubble universes might not have a Big Bang at all in the traditional sense. Some might expand and collapse so quickly that nothing stable could ever form. Most would be utterly hostile to anything resembling chemistry, let alone life. And all of them together, if eternal inflation is correct, would form a structure so vast it makes the observable universe look infinitesimal in comparison. This is what happens when you take cosmology seriously. The answer to whether space ends turns into an answer about whether there is only one universe. And current physics cannot confirm or deny the multiverse. Because by definition, other bubble universes are outside our horizon and causally disconnected from us. No signal from them has ever reached us. No signal ever will. They are, in the most precise physical sense, beyond the edge of what we can know. There are theorists who take the multiverse seriously as a physical prediction. If eternal inflation is a real physical process, they argue, then the multiverse is not speculation. It's a consequence. It follows from the equations as directly as the orbit of a planet follows from Newton's laws. There are other theorists who view the multiverse as a mark against any theory that predicts it, not because they object to vast structures, but because a theory that produces infinitely many unobservable universes, with all possible laws of physics, can explain anything. A theory that explains anything predicts nothing. And a theory that predicts nothing isn't science. This is one of the genuinely unsettled debates at the frontier of cosmology. Not about the data. The data we have is solid. About what counts as a valid scientific explanation. About where physics ends and metaphysics begins. About whether the question "does space end" even has an answer we could recognize as an answer. But even staying within our observable universe, there's another limit worth understanding carefully. Not a limit on space, but a limit on what we mean when we ask about the boundary of the universe. When people ask where the universe ends, they often imagine something like a wall, a boundary where space stops, and beyond the boundary, there's nothing, or some other kind of stuff, whatever that means. But this intuition runs into an immediate problem. If there's a boundary to the universe, what is the boundary a boundary with? What's on the other side? If you answer nothing, you've created a paradox. A boundary between something and nothing is still a location. A place you can stand on one side of and look toward the other. In physics, that requires spatial structure, which is itself more space. If you answer something, then the universe isn't all there is, and we're back to the question of what that something is and where it ends. The honest physical response is that the question contains an assumption that may simply be wrong. The assumption that the universe is a thing inside something else. That it has an exterior. General relativity doesn't require an exterior. It describes space-time as a four-dimensional manifold, a geometric structure that doesn't need to be embedded in anything. Consider the surface of a sphere again. A sphere's surface is a two-dimensional manifold. It has a definite geometry, a definite area. You can move along it in any direction and define distances and angles between points. But to do any of that, you don't need a surrounding three-dimensional space. A being who lived entirely within the surface, who had no concept of up or down relative to the sphere, could still measure that their universe was curved by doing geometry, by drawing triangles and measuring whether the angles added up to 180 degrees. If they didn't, if they added up to more, the being would know they lived on a positively curved surface, even without ever stepping off it to look from the outside. Similarly, the universe doesn't need to be inside anything. It doesn't need an exterior. It can simply be all there is. A self-contained geometric structure that includes everything. Every point, every direction, every moment in time. No outside. Not because the outside is empty or off limits, but because outside is not a concept that applies. When you ask what's beyond the edge of the universe, you may be asking a question like asking what's north of the North Pole. Not a question that has no answer, because the answer is hard to find. A question that has no answer, because the geometry doesn't support the question. The North Pole is a point on a sphere. Every direction from it is south. There is no north. Not because north is blocked, but because the geometry of the sphere doesn't produce a direction called north from that particular location. The universe may work the same way, not because the universe is shaped like a sphere, but because the concept of beyond the edge may not correspond to anything that exists. There's a scale problem that runs through all of these ideas, and it's worth confronting directly. When we talk about the observable universe, the multiverse, the geometry of space, we're talking about things so large that every comparison we reach for falls apart. The Milky Way contains somewhere between 200 and 400 billion stars. Our nearest neighboring galaxy, the Large Magellanic Cloud, is about 160,000 light-years away. The nearest major galaxy, Andromeda, is 2.5 million light-years away. The observable universe contains roughly 2 trillion galaxies. That number, 2 trillion, is a 2 followed by 12 zeros. And the total number of stars in the observable universe is estimated at around 1 followed by 24 zeros. That's a septillion. A number so large that if you spent 1 second on each star, you'd need 30 times the current age of the universe to get through them all. And the observable universe is, by almost any measure of what lies beyond it, a tiny fraction of what's out there. In models based on inflation, the total universe is estimated to be at least 10 to the power of 23 times larger than the observable portion. That estimate comes from the expected expansion during inflation and is almost certainly a dramatic underestimate of the true figure, if the universe is infinite. These numbers don't map onto human intuition. We evolved to track patterns over distances measured in meters, to plan over timescales of days and seasons. Nothing in our cognitive toolkit prepared us for the scale of what we're actually embedded in. And yet, against all expectation, we can reason about it. We can build instruments sensitive enough to detect light from 14 billion years ago. We can derive the geometry of space from temperature fluctuations of 1 part in 100,000. We can calculate the age of the universe to within less than 1% uncertainty. That's one of the stranger facts about the situation we're in. The universe is incomprehensibly large. And somehow, it produced minds that can comprehend it, at least partially, at least mathematically, at least enough to sit with these numbers and ask reasonable questions about what they mean. The cosmic microwave background is worth staying with for a moment, because it's where the most concrete data about these questions lies. When Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey in 1965, they were using a large horn antenna and kept picking up a persistent hiss of noise from all directions. They couldn't eliminate it. They cleaned the antenna. They removed a pigeon nest from the horn, along with the associated mess. The noise persisted. Eventually, they connected with theorists who told them what they were hearing. The afterglow of the Big Bang. The cosmic microwave background radiation. Light from 380,000 years after the beginning of the universe, stretched by expansion over billions of years into microwaves, filling the sky uniformly in every direction. Penzias and Wilson received the Nobel Prize in Physics in 1978 for that discovery. The fact that they stumbled onto it while trying to get rid of what they thought was antenna noise is one of the more pleasing accidents in the history of science. Since then, the COBE satellite in the early 1990s, WMAP in the 2000s, and Planck from 2009 onward have mapped this ancient light with increasing precision. What they found is a sky of extraordinary uniformity. The temperature of the cosmic microwave background is 2.725 degrees Kelvin, 2.725 degrees above absolute zero. And it varies from that temperature by only about 1 part in 100,000, across the entire sky, in all directions. This uniformity tells us that the early universe was almost perfectly homogeneous. The same density, the same temperature, the same physics everywhere. The tiny variations, the ripples at that 1 in 100,000 level, were the seeds of everything. Slightly denser regions attracted more matter gravitationally. Gravity amplified the fluctuations over time. Over hundreds of millions of years, those slight overdensities collapsed into the first stars, the first galaxies, the first galaxy clusters, the cosmic web of filaments and voids that structures everything we see today. Every galaxy, every star, every planet, everything that has ever existed, grew from fluctuations in the cosmic microwave background that were smaller than 1 part in 100,000. That's how the universe works. Tiny differences, compounded over billions of years by gravity, produce structures of breathtaking scale and variety. The COBE satellite, launched in 1989, made the first detailed measurements of those temperature fluctuations. Before COBE, we knew the cosmic microwave background was there. We knew it was uniform. But we didn't know if the fluctuations were actually present at the level theory predicted. When COBE's team, led by George Smoot and John Mather, announced their results in 1992, the reaction in the scientific community was remarkable. Stephen Hawking called it the discovery of the century, if not of all time. George Smoot described looking at the data for the first time as like looking at the face of the universe. It was the direct observational confirmation that the early universe had the structure needed to produce everything we see today. Smoot and Mather received the Nobel Prize in Physics in 2006 for that work. WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, produced the first high-resolution, full-sky map of those fluctuations. It nailed down the age of the universe at about 13.7 billion years, confirmed the flat geometry, and established that ordinary matter is only a small fraction of the total, with dark matter and dark energy making up the overwhelming majority. Planck later refined those proportions to roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. And Planck, launched in 2009 by the European Space Agency, refined all of these measurements further. Planck measured the age of the universe as 13.813 billion years, with an uncertainty of less than 1%. It produced a temperature map of the cosmic microwave background with angular resolution better than 10 arc-minutes, fine enough to resolve individual sound waves that were propagating through the early universe before the fog lifted. Those sound waves, called baryon acoustic oscillations, are imprinted in the cosmic microwave background and also in the distribution of galaxies today. They serve as a standard ruler, a fixed physical scale that we can use to measure distances across the universe and probe the expansion history. The data from the cosmic microwave background is the foundation on which modern cosmology stands. Without it, questions about whether the universe is finite or infinite, flat or curved, old or young, would be unanswerable. With it, we've pinned down the basic parameters of the universe to remarkable precision. And what those parameters tell us, consistently and robustly, is that the universe we live in is flat, old, mostly made of things we don't fully understand, and expanding faster and faster. Which brings us back to the question of whether it ends. There is a detail about the cosmic microwave background that connects directly to that question. If the universe was small enough and had the right topology, you'd expect to see repeated patterns in the cosmic microwave background. Because looking in opposite directions, you'd be looking at the same physical location from different angles. Like standing in a mirrored room and seeing reflections of reflections, but in the geometry of space itself. Specific predictions exist for what those patterns would look like. Pairs of matching circles, found at the same temperature pattern but at different positions in the sky. The Planck team searched for these signatures carefully. The statistical techniques involved are sophisticated. You're looking for correlations across the entire sky, comparing temperature patterns on circles of all possible angular radii. No statistically significant signal was found. The sky doesn't show the repeated patterns that a small finite universe with non-trivial topology would produce. The absence of that signal doesn't prove the universe is infinite. It means that if the universe does loop back on itself, it loops back on a scale larger than the observable universe. Larger than about 80 billion light-years across. Anything smaller, and we'd have seen the signature. The universe is, at a minimum, larger than what we can see, by definition. But Planck's non-detection means it's also larger than the doubled observable sphere, which means the universe is, at the very minimum, enormously larger than what we've been able to observe. Most cosmologists expect the actual universe to be vastly larger than that minimum. Some expect it to be infinite. The data doesn't tell us which. It just keeps pushing the possible boundary outward every time we look more carefully. Let's think about what it would actually be like to travel outward. Not at the speed of light. Just in the most direct physical sense. If you could step into a spacecraft tomorrow and point it at the edge of the observable universe, and if you had unlimited time and unlimited fuel, what would you find as you went? For the first 100 light years or so, you'd pass through the local neighborhood of stars. 100 billion years of stellar evolution, visible in the different ages and types of stars around you. For the first 100,000 light years, you'd traverse the Milky Way. You'd pass through the disk, maybe through one of the spiral arms, outward toward the edge of the galaxy's stellar distribution. Beyond that, for the next few million light years, you'd be in the void between the Milky Way and its satellite galaxies, the Magellanic Clouds. Smaller dwarf galaxies gravitationally bound to us. Tenuous streams of gas connecting them. Beyond that, for millions more light years, you'd approach Andromeda, the local group. The small cluster of galaxies gravitationally bound together that we're part of. Beyond the local group, for tens of millions of light years, you'd enter the Virgo supercluster, the larger structure that contains the local group. And beyond that, you'd enter the cosmic web. Filaments of galaxies stretching between massive clusters with vast empty voids between them. As you went, the pattern would repeat. More galaxies, more filaments, more voids. The universe would look, on the largest scales, statistically the same. No region would look dramatically different from any other. No part of the sky would show you something qualitatively new. The same kinds of galaxies. The same filamentary structures. The same voids. The same statistics. You might travel for billions of light years without anything categorically different presenting itself. And at some point, you'd approach the horizon. The surface from which we first received light. The cosmic microwave background. Not a physical surface. Not a wall of any kind. Just the boundary beyond which matter was still opaque. Still fog. And if you crossed that boundary, in principle, you'd find the universe continuing. Older regions. Earlier states. The distribution of matter getting smoother and more uniform the earlier in time you were looking, until you approached the conditions of the earliest moments. The moments before inflation. The moment before time itself, if that phrase even means anything. The universe would simply continue, as far as we can tell, all the way to the beginning. And beyond the beginning, physics runs out. The cosmic web itself deserves attention because it reveals something important about how space is filled on the largest scales. The universe is not a uniform distribution of matter. It has architecture. Matter is arranged in an intricate three-dimensional web. Vast sheets and filaments of galaxies spanning hundreds of millions of light years, surrounding enormous empty regions called voids. The filaments intersect at nodes where the densest galaxy clusters sit. The whole structure looks, in computer simulations, like a cosmic sponge, or like the interior structure of bone, or like foam, interlocking strands and sheets with hollow spaces in between. The voids are genuinely vast. The Boötes void is roughly 330 million light-years across and contains almost no galaxies. It's not empty in the literal sense. There's still dark matter, radiation, cosmic microwave background photons passing through. But in terms of luminous matter, the stars and galaxies we normally think of as filling space, it's essentially a hole. The Sloan Great Wall, identified in 2003 using data from the Sloan Digital Sky Survey, is a sheet of galaxies extending roughly 1.37 billion light-years. At the time it was found, it was the largest known structure in the universe. The Hercules Corona Borealis Great Wall, identified in 2013, may extend up to 10 billion light-years. If confirmed, it would be the largest known structure in the observable universe. These very large structures pose an interesting challenge. The standard model of cosmology, called lambda cold dark matter, predicts that on scales above about 1 billion light-years, the universe should look smooth and uniform, homogeneous, the same in all directions and at all locations. This is called the cosmological principle. If that principle holds, then the very largest structures we observe are near the limit of what should exist. Structures larger than a few billion light-years would sit in tension with it. Whether the Hercules Corona Borealis Great Wall actually challenges the cosmological principle is still actively debated, but the fact that we're even asking the question tells you something about where cosmology sits right now. We have an extraordinarily successful model, built on decades of observations and refined by extraordinary instruments. And we're testing its limits, finding the places where it might need revision, where new physics might hide. That's not a failure of the model. That's science working exactly as it should. One of the more counterintuitive aspects of the universe on very large scales is that structure doesn't keep going forever in the same way. There appears to be a maximum scale above which there's no more structure. No filaments that just keep getting bigger and bigger without limit. The cosmic web has a characteristic scale, set by the same baryon acoustic oscillations we mentioned earlier. Those pressure waves in the early universe created a preferred scale in the distribution of matter, a scale of about 500 million light-years. Galaxy clusters are slightly more likely to be found at multiples of that separation than at other separations. This tells us that the largest structures are a consequence of the initial conditions and the physics of the early universe, not an arbitrary fractal that continues forever. The universe has texture, but not infinite texture. There's a scale above which it becomes statistically smooth. And this is important for the question of whether it ends. Because it means that even if space is infinite, matter isn't arranged in more and more complex structures without limit. The very large-scale universe, the universe at scales of tens or hundreds of billions of light-years, would look like a uniform sea of galaxy clusters and filaments. Statistically, the same everywhere. No special center. No special edge. No direction that looks fundamentally different from any other. If the universe is infinite, it's infinite in the most straightforward possible way. More of the same, everywhere, without end. Beyond the cosmic web and the edges of the observable universe, there is the question of what physics actually governs the deepest structure of space. Because even within the observable universe, space doesn't behave the same at all scales. At the scales of galaxies and clusters, general relativity is the governing framework. Space-time curves in response to mass and energy. Objects follow geodesics, the shortest paths through curved spacetime. Gravity is not a force in the Newtonian sense, but a consequence of geometry. At atomic and subatomic scales, the relevant framework is quantum mechanics. And here, space has a different character. Space isn't just a passive backdrop. It seethes with quantum fluctuations. Virtual particle pairs constantly appearing and disappearing, existing for vanishingly brief moments before annihilating each other. This isn't metaphor. It has measurable consequences. The Casimir effect, first predicted in 1948 by Hendrik Casimir, arises from the quantum vacuum. Two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force. not from any conventional electric or magnetic field, from the suppression of certain vacuum fluctuations in the space between them. The plates shadow each other from certain wavelengths of vacuum fluctuation, reducing the energy density between them relative to the energy density outside. The result is a tiny but measurable force. It's been confirmed experimentally many times. The quantum vacuum has real, measurable, physical effects. And this raises a deep problem. Quantum field theory predicts that the energy of the vacuum should be enormous. The sum of all the zero-point energies of all the quantum fields, filling all of space. By some estimates, the predicted vacuum energy density exceeds the observed value of dark energy by a factor of around 10 to the power of 120. A 1 followed by 120 zeros. This is sometimes called the worst prediction in all of physics. Not because the theory is wrong in a simple way, but because it suggests there's a cancellation happening of extraordinary precision between different contributions to the vacuum energy, and we have no idea why. We know there's energy in the vacuum. We know it's causing the universe's expansion to accelerate. But the mismatch between the naive theoretical prediction and the observed value is so extreme that it tells us there's something fundamental about the vacuum of space that we don't yet understand. Something deeply important is missing from our picture. And that gap in understanding connects to the deepest version of the question we started with. Because in quantum gravity, the theories that attempt to unite general relativity with quantum mechanics, space itself may not be fundamental. It may emerge from something more basic. String theory suggests that particles and forces are the excitations of tiny, one-dimensional strings, vibrating in a space that may have 10 or 11 dimensions. The extra dimensions beyond the 3 we experience would be curled up at scales too small to detect. Loop quantum gravity suggests that space itself is discrete at the smallest scales. Not a continuous smooth manifold, but a network of quantum nodes connected by links with areas and volumes that come in discrete units. Volume is not infinitely divisible. Space is granular. In both of these frameworks, what we experience as smooth, continuous space, the space that we're asking whether it ends, is an approximation. A large-scale average behavior of something more fundamental that operates at scales far below anything we can currently probe. The Planck length, approximately 1.6 times 10 to the power of -35 meters, is the scale at which physicists expect space-time to lose its smooth, continuous character, to become granular, to dissolve into discrete quantum events with no clean geometric structure between them. At that scale, asking whether space is this distance from that point may not be a well-defined question. The concept of location might break down. If space is not fundamental, then asking where it ends is like asking where the temperature of a gas ends. Temperature is a real property of the gas. But temperature isn't a fundamental ingredient. It emerges from the collective behavior of a huge number of molecules. If you zoom in to a single molecule, temperature doesn't apply. It's not that the temperature ends. It's that the concept breaks down below the scale at which it's valid. Space might be the same. A valid concept at everyday scales, at stellar scales, at galactic scales. But not a valid concept at the Planck scale. Not fundamental. Emergent. Built from something deeper that we don't yet have a name for. The theory of quantum gravity remains incomplete. Some of the most technically accomplished minds in physics have been working on it for decades. There are partial frameworks, promising mathematical structures, deep insights. But a complete theory that makes definitive, testable predictions about the nature of space at the smallest scales doesn't exist yet. Which means the deepest version of the question, whether space ends, can't be answered at the level of fundamental physics. Not yet. Possibly not for a long time. There is a version of this question that's been with us for much longer than modern cosmology. Philosophers have been asking about the limits of the universe for thousands of years. In the 5th century before the Common Era, a philosopher named Archytas of Tarentum posed a version of it that still works. "Stand at the edge of the universe," he said, "and reach your arm out." What does your arm reach into? If your arm reaches into space, then there's more space, and you're not at the edge. If your arm can't reach out, something is stopping it, and that something is part of the universe too. You can't be at the edge. This argument was used for centuries to argue that the universe must be infinite. It doesn't prove the universe is infinite, but it does show that the concept of a spatial edge creates immediate paradoxes. Aristotle disagreed with the conclusion. He believed the universe was finite and that space itself didn't continue beyond the outermost sphere of the cosmos. His answer to Archytas was essentially to deny the premise. Space, for Aristotle, wasn't a container that matter sits inside. Space was relational. The distances and volumes defined by matter and its relationships. Without matter, there is no space. A view that turns out to be closer to Einstein's general relativity than to Newton's absolute space. Giordano Bruno, in the 16th century, argued passionately for an infinite universe with no center and no edge. He held that the stars were distant suns, each potentially with worlds of their own. An infinite universe, he said, was the only idea worthy of an infinite creator. We won't be invoking that framing tonight. But what Bruno was describing, a boundless universe of countless suns, was closer to what we actually observe than the picture his contemporaries defended. He was burned at the stake in 1600. Not specifically for his cosmological views, but they formed part of the charges against him. Science sometimes advances at a painful cost. Newton's mechanics implied an infinite static universe. But Newton worried about the consequences. In an infinite universe, with matter distributed throughout, every point would experience gravitational pulls from all directions. Any slight imbalance would cause collapse. Newton could not entirely satisfy himself that such a universe would be stable. He was right to worry. An infinite static universe, with matter distributed through it, is gravitationally unstable. It was Einstein who finally gave the problem a framework in which these questions could be asked with mathematical precision. He tried, initially, to produce a static universe by introducing a term called the cosmological constant into his equations, a repulsive term to balance the gravitational attraction. He later called this his greatest blunder, when Hubble's observations made clear the universe was not static, but expanding. The cosmological constant was eventually resurrected, in a different form, to explain the accelerating expansion we observe today. Dark energy, in mathematical terms, acts like a cosmological constant. Einstein's blunder turned out to be right, just for different reasons than he thought. And it was Hubble's discovery in the 1920s that galaxies were receding from us and that the universe was expanding, that turned the philosophical question into an empirical one. A question we could actually take to the sky and try to answer with instruments and data, from Archytas to Einstein to Planck. The question is the same. The tools have changed everything. There's one more thing worth exploring before we bring this together. The question of whether space ends isn't only about the external boundary of the universe. It's also about the internal structure of space. Whether space is smooth or granular, whether it can be divided infinitely finely, or has a minimum unit. We've touched on the Planck length already, but there's a related question that comes up in the study of singularities. Singularities are points where the equations of general relativity break down, where density becomes infinite and our mathematical description fails. The most famous singularity is at the center of a black hole. When a massive star collapses at the end of its life, if it's massive enough, nothing can stop the collapse. The core implodes. Gravity overwhelms all other forces. The matter compresses without limit. General relativity predicts a singularity, a point of infinite density. The beginning of the universe, the Big Bang, itself, is also described by general relativity as a singularity, a state of infinite density from which space and time emerged. Physicists generally believe that the singularities in general relativity are not physically real. They're a signal that the theory has exceeded its domain of validity. At the extreme densities near a singularity, quantum gravity effects become important. And a complete theory of quantum gravity would presumably replace the infinite density with something finite, something physically sensible. What that replacement looks like is unknown. Some approaches to quantum cosmology, like the no-boundary proposal developed by Stephen Hawking and James Hartle, suggest that time itself becomes indistinguishable from space near the Big Bang. In this picture, asking what came before the Big Bang is like asking what's south of the South Pole. The question has no answer, not because something is hidden, but because the geometry doesn't support the question. Time has a boundary in one direction, 13.8 billion years ago, where the geometry becomes such that the concept of before loses meaning. And space may have an analogous situation in the spatial directions. Not a wall, not an edge, but a point where the geometry changes character so fundamentally that the question of what's beyond can't be formed. These ideas are speculative. They are the frontier, but they point towards something important. The question of whether space ends may not be resolved by finding a boundary. It may be resolved by understanding why boundaries are the wrong concept to reach for. Let's talk about dark matter for a moment, because it plays a role in the structure of the universe that connects to everything we've been discussing. Dark matter is matter we can't see. It doesn't emit light. It doesn't absorb light. It doesn't interact with ordinary matter except through gravity. And yet, it makes up approximately 27% of the total energy content of the universe. More than 5 times the amount of ordinary matter. We know dark matter exists because we can measure its gravitational effects. Galaxies rotate in ways that can only be explained if there's far more mass present than we can see. Galaxy clusters bend light far more than their visible mass would predict through a process called gravitational lensing. The formation of large-scale structure in the universe, the cosmic web of filaments and voids, matches observations only if dark matter is included in the models. Without dark matter, galaxies wouldn't have formed as quickly as they did. The universe would look fundamentally different. What dark matter actually is remains one of the biggest open questions in physics. The most popular candidates are weakly interacting massive particles, hypothetical particles that interact via gravity and the weak nuclear force, but not electromagnetism or the strong force. No such particle has been detected directly, despite decades of searching. Other candidates include axions, hypothetical, very light particles, originally proposed to solve a problem in particle physics, and primordial black holes that might have formed in the early universe before stars existed. None of these candidates has been definitively confirmed. Dark matter is not a comfortable placeholder. It's a genuine gap in our understanding. And because dark matter makes up more than a quarter of everything in the universe, that gap is significant. Dark matter is distributed throughout the universe. Every galaxy sits inside a dark matter halo, a roughly spherical distribution of dark matter extending far beyond the visible galaxy. The dark matter halos of large galaxies extend for hundreds of thousands of light-years beyond the visible edge of the disk. And the cosmic web of filaments and voids is built, at its foundation, by the distribution of dark matter. Ordinary matter falls into the gravitational potential wells carved out by dark matter. The visible universe is a luminous decoration on a dark matter skeleton. Understanding what dark matter is would change our understanding of the structure of the universe. It might change our understanding of space itself if dark matter turns out to be something more exotic than a new particle. It might point toward new physics that modifies gravity at large scales, or toward a deeper theory in which ordinary matter and dark matter are different faces of the same underlying structure. We don't know. The honest answer is we still don't know. One of the most philosophically interesting aspects of the question of whether space ends is what the answer would mean if we could find it. Suppose, hypothetically, that we discovered tomorrow that the universe is infinite. An actual infinity. Not just very large. Actually, genuinely, mathematically infinite. What follows from that? In an infinite universe, if matter is distributed uniformly at large scales, as observations suggest it is, then every configuration of matter that can exist does exist somewhere. Given infinite space with a finite density of matter, and quantum mechanics allowing only a finite number of distinguishable states in any finite volume, any arrangement of matter you can specify must be repeated infinitely many times in an infinite universe, including the arrangement of matter that constitutes you. Reading this. Right now. Infinitely many copies. Some identical. Some differing by one atom. Some differing in ways large enough that their version of this moment plays out entirely differently. This is called the Level I multiverse by cosmologist Max Tegmark. It's not a separate universe. It's just the consequence of infinite space with a finite density of matter. The copies can't contact each other. The distances between them are incomprehensibly large, but they exist if the universe is infinite. Now consider what it would mean if we discovered the universe is finite. A closed universe with positive curvature, a defined total volume, a finite number of galaxies, a finite number of stars, a finite number of atoms. That would mean there is a fact of the matter about the total content of the universe. A finite list, in principle, of everything that exists. No infinite repetition. No copies. Every configuration of matter that exists exactly as many times as the physics of this particular universe produced it. Maybe once. Maybe not at all. The universe would be, in a sense, more modest, more contained, more specific? Either answer would change how we think about what it means to exist, what it means to be particular, what it means to be here, in this specific arrangement, rather than some other. These aren't idle philosophical musings. They're consequences of taking physics seriously, taking the question seriously enough to follow it to where it leads, which is one of the things science does that nothing else quite manages. It keeps answering the question behind the question, all the way down until you're somewhere you didn't expect to be. The light from the most distant things we can see is already a kind of ghost, and yet that inference is solid. The physics that describes what we can see is the same physics that should describe what we can't. The laws don't change at the horizon. The expansion doesn't stop at the horizon. The matter doesn't vanish at the horizon. It just continues, beyond our ability to confirm, but fully consistent with continuing. That's the basis on which cosmologists speak with confidence about a universe vastly larger than what we've observed. Not speculation, extrapolation from known physics. And known physics, tested to extraordinary precision, says space goes on. We've been building toward a kind of answer all night. And the answer is honest, if not entirely satisfying. The observable universe ends at about 46 billion light-years. That boundary is real. It's the boundary set by the age of the universe and the speed of light. The actual universe almost certainly continues beyond that. The best measurements we have suggest it's either extremely large and flat or truly infinite. There's no observed boundary, no detected wall, no known physics that requires space to stop anywhere. If space ends, we don't know it. And if space ends in the way that matter ends at an edge, a sharp boundary beyond which there is nothing that appears to be inconsistent with general relativity, which doesn't permit such structures, without specific matter and energy distributions, we have no evidence for. At the deepest level, space may not even be the kind of thing that can end, in the way we imagine when we picture a wall. If space is emergent, if it arises from something more fundamental at the Planck scale, then the question of whether space ends may dissolve into a deeper question about the underlying structure that produces space. A question we can't yet answer because we don't have the theory. What we do know is this: the universe is vastly larger than what we can see. It may be infinite. It appears to be the same everywhere we can look. It began from a state that general relativity calls a singularity, and that quantum gravity will eventually explain differently. And it has been expanding since that beginning, faster and faster, carrying the visible horizon closer and closer in terms of what fraction of the whole we can access. We are not at the center of the universe. There is no center. We are not in a special location. We are one of trillions of possible vantage points, all of which would see an observable universe of similar size and similar content. We are, from the universe's perspective, if the universe has a perspective, unremarkable. And from our perspective, the universe is everything. What strikes me most about this question, when I sit with it long enough, is that the uncertainty itself is remarkable. We have mapped the cosmic microwave background to 1 part in 100,000. We have detected gravitational waves from merging black holes billions of light-years away. We have imaged the shadow of a supermassive black hole at the center of a distant galaxy. We have catalogued the positions of millions of galaxies, and used them to trace the expansion history of the universe. And after all of that, the answer to whether space ends is, we don't know. Not because we haven't looked hard enough, because the universe may be infinite. And you can't observe infinity. You can only ask whether infinity is consistent with what you do observe. And it is. Completely. The universe behaves exactly as you'd expect an infinite or near-infinite space to behave, with a visible horizon set by the age and expansion history, with a structure that's statistically uniform at the largest scales, with an expansion that shows no sign of encountering any boundary. The universe is not hiding its edge from us. As far as we can tell, there is no edge to hide. There's a number that comes up again and again in cosmology, and it's worth confronting directly. 10 to the power of 122. That's the ratio some physicists calculate between the energy density of the vacuum predicted by quantum field theory and the energy density of the vacuum we actually observe. A 1 followed by 122 zeros. This is not a rounding error. It's not a sign that the theory is almost right. It's a sign that something is fundamentally wrong in our understanding of how quantum mechanics and gravity interact. And it matters for the question of space, because the vacuum energy, dark energy, is what's causing space to expand. If the vacuum energy were 122 orders of magnitude larger than it is, the universe would have expanded so violently in its earliest moments that no structure could have formed. No galaxies. No stars. No atoms. Space would be expanding so rapidly that the distances between subatomic particles would grow faster than the forces between them could maintain any contact. Chemistry would be impossible. The universe would be an eternally expanding gas of elementary particles, rapidly diluting into nothingness. If dark energy were even modestly larger than it is, gravitationally bound structures would be ripped apart before they could form. If it were modestly smaller or negative, the universe might have collapsed back on itself long before stars had time to form and live out their lives and scatter their heavy elements. The value of dark energy, we observe, incomprehensibly small relative to the theoretical prediction, but not zero, sits in a range where galaxies can form, stars can burn, planets can exist. Some physicists take this as evidence for the anthropic principle. In a multiverse with many different values of dark energy across different bubble universes, we find ourselves in a bubble where the value permits our existence, because that's the only kind of bubble we could find ourselves in. Only in universes with compatible dark energy values could observers evolve to ask the question. Others find this deeply unsatisfying. The anthropic argument feels like giving up. Like saying, the reason the universe is the way it is that we're here to notice, which is circular. Most physicists hope for a deeper explanation. Some fundamental reason why the vacuum energy takes the value it takes. Some symmetry or principle or mechanism that fixes it to a small value, rather than the enormous value quantum field theory naively predicts. No one has found that explanation yet. The cosmological constant problem remains one of the deepest unresolved issues in all of theoretical physics. And it sits at the intersection of the two greatest theories we have, general relativity and quantum mechanics. The two theories that, when combined, start producing predictions that can't all be right. The inconsistency tells us there's something we're missing. Something important. Something that may, when we find it, change our understanding of what space is. Let's spend some time with black holes, because they're relevant to the question in a way that isn't immediately obvious. A black hole is a region of space-time where the curvature becomes so extreme that not even light can escape. The boundary surrounding that region is called the event horizon. Cross the event horizon and you can't get back out. Not because a force is pulling you in, but because all future directed paths in space-time led inward. There is no direction, in space or time, that leads back outside. The geometry itself closes off. Black holes form when massive stars exhaust their nuclear fuel and their cores collapse. If the mass is large enough, nothing can stop the collapse. Not the pressure of hot gas. Not electron degeneracy, pressure. Not neutron degeneracy, pressure. The collapse continues until general relativity predicts a singularity, a point of infinite density. But black holes also form at the centers of galaxies. Supermassive black holes, with masses ranging from hundreds of thousands to billions of times the mass of the Sun, sit at the centers of most large galaxies, possibly all of them. Our own Milky Way has a supermassive black hole at its center. It's called Sagittarius A. It has a mass of about 4 million suns. In April of 2019, the Event Horizon Telescope collaboration published the first direct image of a black hole's shadow, not Sagittarius A. The supermassive black hole, at the center of the galaxy M87, 55 million light-years away. That black hole has a mass of about 6.5 billion suns. Its event horizon is larger than the entire orbit of Pluto around the Sun. The image, an orange and black glowing ring, was made by coordinating radio telescopes across the entire planet to create an effective telescope the size of Earth. 3 years later, in May of 2022, the Event Horizon Telescope published the first image of Sagittarius A itself, our own galaxy's central black hole. The image showed the same kind of glowing ring, the shadow of the event horizon against the bright accretion disk of material spiraling in. These images are not just beautiful. They're direct confirmations that black holes exist. That space-time curvature, extreme enough to trap light, is real. That general relativity accurately describes the most extreme gravitational environments we know of. Now, black holes create a boundary within space, a region from which nothing can return. Does that mean space ends at the singularity inside a black hole? Probably not. In the same sense, we're asking about the edge of the universe. But black holes do create a local limit, an information barrier. Once matter crosses the event horizon, whatever happens to it inside is causally disconnected from the exterior universe. The interior of a black hole is not accessible, not in principle, not even in theory. Everything that falls in is lost to the outside universe, or so it appears. Stephen Hawking's work in the 1970s showed that black holes aren't entirely black. Quantum effects cause them to radiate, very slowly, very faintly. This process, Hawking radiation, means that over an extraordinarily long time, black holes gradually lose mass and eventually evaporate. And here's where it gets strange. When a black hole evaporates, what happens to the information about everything that fell in? If the Hawking radiation is completely random, carrying no information about what went in, then that information is destroyed forever. But quantum mechanics says information can't be destroyed. This is the black hole information paradox. and it's been one of the most productive problems in theoretical physics for 50 years. The resolution of it, whatever form it takes, will likely require a fundamental revision of how we think about space, time, and information. Some recent work suggests that the interior of a black hole might be connected to the Hawking radiation through structures called quantum error-correcting codes, or through wormholes in space-time, or through a kind of holographic encoding where all the information about the interior is somehow encoded on the event horizon. These ideas are provisional, but they suggest that the boundary of a black hole is not a wall where space ends. It's a surface where the relationship between space, information, and quantum mechanics becomes radically different from anything we experience outside. Space doesn't end at the event horizon, but physics changes character there in ways we're still working to understand. The stars themselves are, in a sense, the universe's primary way of making complexity. They're the furnaces where simple hydrogen and helium get converted into the heavier elements: carbon, oxygen, iron, calcium, and phosphorus. Everything in the periodic table above helium was made inside a star, or in the explosions of stars, or in the violent mergers of neutron stars. Every atom of carbon in your body was forged in the nuclear furnace of a star that no longer exists. That star lived its life, burned through its hydrogen, expanded into a giant, shed its outer layers, and left behind a stellar remnant. And in the process, it scattered those carbon atoms into space, where they drifted for millions of years, joined other clouds of gas, formed new stars, new planetary systems, eventually found their way into you. The stuff you're made of has a history, not just a biological history, a stellar history, an astronomical history. Those atoms have been inside stars. They've been scattered through interstellar space. They've been part of molecular clouds. They've been incorporated into planetary bodies. They've been cycled through geological processes. And now they're arranged, temporarily, in the specific configuration that is you, considering these thoughts. The universe, in a very real sense, is not just the stage where life happens. It's the factory that produces the ingredients for life and the context in which life makes sense. This connection between the large-scale structure of the universe and the existence of complex structures within it runs deeper than it first appears. The flatness of the universe, which we measure to be remarkably close to the critical density, isn't just a geometric fact. It's a precondition for the existence of stars. A universe significantly denser than ours would have collapsed back on itself before stars had time to form and live. A universe significantly less dense would have expanded too fast for matter to accumulate into the dense clumps that become galaxies and stars. The constants that govern nuclear physics, the strong force, the electromagnetic force, are set to values that allow hydrogen to fuse into helium at the temperatures found inside stellar cores. Slightly different values would make stars burn differently, or not at all. Whether this fine-tuning points to a multiverse, or to some deeper principle we haven't discovered, or to something else entirely, is one of the most actively debated questions in theoretical physics. But the fact that the universe has the large-scale properties it has, that space is as large and old and correctly proportioned as it is part of why any of this, the stars, the planets, the chemistry, the biology, the question, is possible at all. The question of whether space ends is not separate from the question of why there are things that can ask the question. They're connected at a level we don't fully understand. The expansion of the universe was first measured precisely by Edwin Hubble in the 1920s, using observations of galaxies made with the 2.5-meter Hooker telescope at the Mount Wilson Observatory in California. Hubble discovered that distant galaxies are moving away from us and that the speed of their recession is proportional to their distance. A galaxy twice as far away recedes twice as fast. This relationship, Hubble's law, implies that the universe is uniformly expanding, every point moving away from every other point. No center. No preferred location. At the time, the dominant assumption in cosmology was that the universe was static. Einstein's general relativity had predicted that the universe should be dynamic, either expanding or contracting. But Einstein had introduced a term into his equations, the cosmological constant, specifically to produce a static universe. Because a static universe seemed physically reasonable. When Hubble's observations made clear the universe was expanding, Einstein removed the cosmological constant and called it his biggest mistake. The expansion Hubble measured was not uniform in the sense of everything moving at the same speed. It was systematic in the sense that recession speed was proportional to distance. Everything receding from everything else, like the pattern you'd see on the surface of a balloon being inflated. Every point on the balloon's surface moves away from every other point. No point is the center of the expansion. And when you ask where the expansion started, the answer is everywhere at once. The Big Bang wasn't an explosion at a point in space. It was an expansion of space itself, happening simultaneously everywhere. There is no location you can point to and say, that's where the Big Bang happened. The Big Bang happened everywhere, at every point that now exists in the observable universe and beyond. This is one of the most conceptually difficult things to absorb about modern cosmology. We're used to thinking of explosions as starting from a point and expanding outward. Fireworks, bombs, even stellar explosions, supernovae, start from a collapsing core and expand outward through space. But the Big Bang wasn't like that. It was space itself beginning to exist and immediately beginning to expand. Every point in that expanding space was, at the beginning, in the same initial state. Hot, dense, nearly uniform. And every point has been expanding away from every other point ever since. There's no outside, no edge from which the expansion is happening inward. Just the expansion itself, happening at every point, in every direction, continuously. Measuring that expansion is one of the central projects of modern observational cosmology. And the measurements have become so precise that we've now identified a tension in the results. Two different ways of measuring the expansion rate give slightly different answers. Measurements of the cosmic microwave background using data from the Planck satellite give a value for the current expansion rate of about 67 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. But measurements using a different method, based on distances to nearby galaxies, calibrated using variable stars called Cepheids, and extended using Type 1a supernovae as standard candles, give a value of about 73 kilometers per second per megaparsec. The difference between 67 and 73 might not sound large, but both measurements are precise enough that the discrepancy is statistically significant. It's called the Hubble tension. and it's one of the most actively discussed problems in cosmology today. It might indicate a systematic error in one of the measurement methods that hasn't been identified yet. Or it might indicate new physics, something beyond the standard cosmological model that affects the expansion history of the universe in a way the current model doesn't capture. Maybe dark energy isn't a constant, but a field that changes over time. Maybe there are additional light particles beyond those in the standard model of particle physics. Nobody knows. Yet, the Hubble tension is one of the reasons cosmologists aren't complacent. The model works extraordinarily well, and there's a persistent anomaly at its edge that might be telling us something important. The universe also has a future, and the future of the universe is, in many ways, as strange as its origin. We're currently about 13.8 billion years into cosmic history. The universe is in what cosmologists call the stelliferous era, the age of stars. Stars are actively forming across the universe. Galaxies are producing new stellar nurseries from their reservoirs of gas. The sky, from any vantage point in the universe, is full of stellar light. But this era will end. The universe is not in a steady state. It's evolving. Star formation requires gas. Gas is a finite resource. As stars burn through their nuclear fuel, they return some of it to interstellar space in stellar winds and explosions. But not all of it. Some fraction gets locked up in stellar remnants. White dwarfs, neutron stars, black holes. Over time, the reservoir of gas available for new star formation depletes. Star formation rates are already declining. The universe was making stars more vigorously 10 billion years ago than it is today. In the distant future, perhaps 100 trillion years from now, the last stars will burn out. The smallest, coolest red dwarf stars live the longest, but even they exhaust their fuel eventually. When the last red dwarf cools and fades, the stelliferous era ends. What follows is the degenerate era. The universe will be populated primarily by stellar remnants. White dwarfs, slowly cooling over trillions of years. Neutron stars. Black holes of all sizes, from stellar mass to the supermassive monsters at galaxy centers. And dark matter, still present everywhere, still providing the gravitational scaffolding, but with nothing left to illuminate. The universe will be dark. Not completely. White dwarfs will glow faintly from their residual heat. Neutron stars will radiate. Occasionally, two compact objects will collide and release a brief burst of energy. But the scale of this luminosity will be incomparably smaller than the era of stars. Over still longer timescales, the degenerate era gives way to the black hole era. White dwarfs and neutron stars eventually decay through quantum processes. The proton itself, if it's unstable as some theories predict, will eventually cease to exist. Matter, as we know it, ordinary baryonic matter, will be gone. Only black holes and the elusive particles that don't decay will remain. And then, the black hole era ends. Black holes, as Hawking showed, radiate. Slowly. The most massive black holes will take an almost inconceivably long time to evaporate. A black hole, the mass of Sagittarius A, would take roughly 10 to the power of 97 years to evaporate through Hawking radiation. A 1 followed by 97 zeros. But eventually, even those colossal black holes will evaporate completely. They'll decay into a burst of Hawking radiation as they approach zero mass. Their final moments, comparatively energetic. The radiation they emit will disperse through an enormously expanded space. This is the dark era, the final state of the universe, as best current physics can project it. A cold, dark, enormously expanded space, populated only by long-wavelength radiation left over from Hawking evaporation and the Big Bang. Maybe a few stable elementary particles, electrons and positrons, so diluted that the average separation between them would be vast. Temperature approaching absolute zero. Entropy at its theoretical maximum. No structure. No chemistry. No gradients. No information processing. Just space, cold and vast, expanding forever under the relentless pressure of dark energy. This eventual fate is sometimes called the heat death of the universe. Not heat in the sense of warmth. Heat in the thermodynamic sense. Maximum entropy. The state where no further work can be done. No energy gradients left to exploit. And expanding. Forever. Getting larger and colder and more dilute without limit. Whether this actually happens depends on whether our current physics is correct over these timescales. It might not be. Dark energy might change over time. New physics might intervene. The proton might not decay. Hawking radiation might work differently than we think. But based on what we currently know, the universe is heading towards something very different from what it is today. And that future state, cold and dark and vast and expanding forever, is itself a kind of answer to the question of whether space ends. Space, in that distant future, will be larger than it is now, by an enormous factor, and still expanding. Space-time, in its final state, would be geometrically unbounded in every direction. An infinite cold expanse of nearly empty space, with nothing left in it that can ask what's beyond the next horizon. It's worth pausing to think about what it means that we can reason about all of this. We live on a small, rocky planet, orbiting an ordinary star in the outer disk of a medium-sized spiral galaxy, itself one of trillions. We are made of atoms forged in the final explosions of stars that no longer exist. We have been capable of abstract reasoning for, at most, a few 100,000 years. We have been doing science, in any systematic way, for about 500 years. We have had access to modern instruments, telescopes capable of detecting the cosmic microwave background, only for about 50 years. And in that time, we've worked out the age of the universe, the composition of the universe, the geometry of space on the largest scales, the origin of cosmic structure, the existence and properties of dark matter and dark energy, the physics of the first 3 minutes after the Big Bang. We've detected gravitational waves. We've imaged black holes. We've built a cosmological model that accurately predicts the large-scale structure of the observable universe with remarkable precision. This is one of the strangest things about the situation we're in. We are very small, very recent, very local, and yet we can do this. We can take a few billion photons from a 13-billion-year-old glow, analyze their temperature fluctuations to 1 part in 100,000, and derive the age and geometry of the entire observable universe. There's no obvious reason this should work. No reason the universe should be comprehensible to creatures that evolved to navigate social relationships in small groups. And yet, it is. The Equations of General Relativity, written down in 1915 by Einstein, without any data about the cosmic microwave background or the large-scale structure of the universe, turn out to describe both with extraordinary accuracy. Quantum mechanics, developed in the 1920s to explain atomic behavior, turns out to have implications for the vacuum energy of space and the origin of cosmic structure. The mathematics we invented to describe things we could see and touch turns out to work in regimes we could not have imagined. This isn't guaranteed. There's no logical necessity for the universe to be ordered in ways that our mathematics can capture. And yet it is. The universe is, at its deepest levels we've reached, mathematical. Its structure is captured by equations. Its behavior follows laws. And those laws are the same everywhere we can look. The same physics that governs the electron in your phone governs electrons in galaxies billions of light years away. The same gravity that holds the Earth in its orbit holds galaxy clusters together. The same nuclear physics that powers our sun powers every other star. The universe is remarkably uniform, not just in its content, in its laws. And that uniformity is part of what gives cosmology its power. We can make observations here and draw conclusions about there. We can measure the cosmic microwave background and learn about the Big Bang. We can detect gravitational waves from merging black holes a billion light years away and confirm the predictions of general relativity in regimes Einstein never imagined. This is the gift that the uniformity of physical law gives us. The ability to study the universe from a fixed position and still learn about the whole. There's one more concept worth exploring carefully. It's called the no-boundary proposal, and it was developed by Stephen Hawking and James Hartle in 1983. It's an attempt to answer what happened before the Big Bang, or more precisely, to dissolve the question. In ordinary physics, time is a dimension. It runs from the past to the future. You can ask what happened at any given moment, earlier or later. At the Big Bang, in the standard cosmological picture, time itself began. This creates an obvious question. What happened before time began? The question feels urgent, but is logically problematic. If time didn't exist before the Big Bang, then before has no meaning. Before is a temporal concept. Without time, there is no before. Hawking and Hartle tried to make this precise using quantum cosmology. They applied the principles of quantum mechanics to the universe as a whole, including space-time itself. In ordinary quantum mechanics, you can ask about the quantum state of a particle. What is the probability of finding it in a given position? Hawking and Hartle asked, what is the quantum state of the universe? What is the probability distribution over different possible geometries of space-time? The answer they found was striking. In the quantum regime, near the origin of the universe, time doesn't behave like a dimension that has a beginning. Instead, it behaves more like a spatial dimension. It becomes rounded off like a sphere. On a sphere, the North Pole is a perfectly ordinary point. Nothing special happens there. But if you try to go further north than the North Pole, you can't. Not because there's a wall, but because further north isn't a direction that exists. The North Pole is the boundary of the northward direction, but it's a smooth boundary. The geometry doesn't have a sharp edge. It doesn't have a singularity. It just rounds off. Hawking and Hartle proposed that the beginning of time is like that. The singularity of the Big Bang, in their picture, is replaced by a smooth quantum geometry where time becomes spatial-like. There is no moment before the beginning. Not because there's an impenetrable barrier, but because the geometry doesn't support the question. Time and space lose their distinct character near the origin, and asking what came before is like asking what's south of the South Pole. Not a question that has an answer, not because we haven't explored there yet, but because the geometry simply doesn't produce a direction called further back. The no-boundary proposal is controversial. It makes specific predictions about the pattern of temperature fluctuations in the cosmic microwave background, predictions that have been debated. It requires quantum gravity, a theory we don't have in complete form, but it represents an attempt to do something important, to take the question of what lies beyond the boundary of time and show that the concept of boundary may not apply, that the question assumes a framework, a sharp beginning with something on the other side that the physics doesn't support. The same move might apply to space. The question, where does space end, assumes that space is the kind of thing that can have an end, a boundary, an edge on the other side of which is something else. But if space is emergent, if it arises from a deeper quantum structure that doesn't have the same kind of geometry, then the question might be dissolved rather than answered. Not, here is the edge of space, but the concept of an edge doesn't apply to space at this level of description. This is philosophically unsatisfying in one sense. We wanted a location, a number, a distance. Here is where it ends. Instead, we get, the question assumes something about the nature of space that might not be true, but it's also deeply honest. It says that reality doesn't always conform to the shapes our intuition reaches for, that the map of our expectations sometimes doesn't match the territory, and that finding out where the map fails is itself one of the most valuable things science can do. There's a specific experimental frontier that brings some of this into focus. The search for primordial gravitational waves. In the very early universe, during inflation, quantum fluctuations in the inflationary field created ripples in space-time itself, gravitational waves. These primordial gravitational waves would have imprinted a specific pattern on the cosmic microwave background, a pattern called B-mode polarization. Detecting B-mode polarization from primordial gravitational waves would be direct evidence that inflation occurred. It would give us information about the energy scale of inflation, how energetic the inflationary process was, which in turn constrains models of inflation, helps us distinguish between different theories about what drove it and what happened at those earliest moments. In March of 2014, a team using a telescope at the South Pole, called BICEP-2, announced they had detected just such a signal. The scientific community reacted with enormous excitement. If confirmed, it would be one of the most important discoveries in cosmology. Direct evidence of inflation. Direct evidence of gravitational waves from the first fraction of a second of the universe. Then, the cautious reassessment came. The signal BICEP-2 detected turned out to be consistent with polarized emission from dust within our own galaxy. The dust contamination hadn't been fully accounted for. The primordial signal, if present, was hidden beneath the dust signal. The excitement faded, but the search continues. More sensitive instruments. Better dust maps. Better analysis techniques. The current frontier is a generation of experiments, including BICEP Array, the Simons Observatory, and the planned CMB S4 experiment. a large-scale cosmic microwave background survey involving many telescopes working together. If inflation happened at the energy scales most favored by current theory, these experiments might detect the B-mode signal. If they don't, it constrains inflation models dramatically. And if they do detect it, we'll have confirmed a process that happened in the first 10 to the power of negative 32 seconds of the universe's history. At energies we'll never be able to recreate in a particle accelerator. We'll be reading the record of the first instant of spacetime's existence, encoded in the polarization of light that has been traveling for 13.8 billion years. This is what modern cosmology can do. It can reach into the very beginning and extract information. And the information it finds speaks directly to the questions we've been asking tonight. About how space came to be. About what drove its initial expansion. About whether that expansion continues elsewhere. Whether the universe we see is one of many. Whether space ends. Let's return to where we started. The night sky. 5,000 stars, visible to the naked eye. Each one a sun. Many of them with planets. Some of those planets probably rocky. Probably in the right temperature range for liquid water. We don't know which ones. We don't know if any of them host life. But we know the ingredients are common. Water. Carbon. Nitrogen. Phosphorus. The basic chemistry of biology is made of the most common elements in the universe. And the conditions that allow that chemistry to operate, liquid water, energy gradients, chemical diversity, are not obviously rare. The universe has produced at least one location, here, where all of this came together, where chemistry crossed over into biology, where biology crossed over into consciousness, where consciousness crossed over into curiosity, into the ability to look up at the sky and wonder, to build instruments and theories and carry the wondering outward, to the edge of what we can detect, and then, a little further, into the territory of inference and extrapolation, into the question of whether space ends, and to sit with the honest answer. We don't know, but we've learned enough to understand why it's hard. We've learned enough to frame the question correctly, to understand the difference between the observable boundary and the possible physical boundary, to understand what inflation implies, to understand what the geometry of space means for the question of endings, to understand that the question may dissolve at the level of quantum gravity into something that doesn't have the sharp edges our intuition reaches for. That's progress. Genuine progress. Even if the answer is still incomplete. The universe is not obligated to be comprehensible. There's no rule that says the questions we ask have to have answers we can access. And yet, consistently, the universe has turned out to be more understandable than we had any right to expect. Not simple, not easy, but understandable. Given enough patience, enough instruments, enough mathematics, enough willingness to follow the equations wherever they lead, the structure of the cosmos yields. It gives up its secrets. One measurement at a time. One observation at a time. One equation at a time. The question of whether space ends is one of the oldest questions humans have asked. And the answer we've built over centuries of observation and theory is that space, as far as we can tell, does not end. It extends in all directions, without any observed limit, without any known physical mechanism that would require it to stop, without any data that points to a boundary. It may be infinite. It may be finite, but without an edge. It may be so much larger than what we can observe that the distinction is practically meaningless. But it doesn't end in the way we picture endings. No wall. No wall. No edge. No line you can cross into nothingness. Just space. Vast and expanding, and, as far as we can tell, endless. So, when you go outside tonight and look up at the sky, try to hold two things in your mind at once. The sky is finite. The bubble of space from which light can reach you has a definite radius of about 46 billion light-years. Everything within that bubble has a finite age, a finite size, a finite history. We can map it. We are mapping it. And at the same time, beyond that bubble, in all likelihood, space continues without end. No wall. No wall. No boundary. No edge. Just more of what you're seeing, endlessly. More galaxies, more stars, more dust and gas and dark matter and dark energy and quantum fluctuations, stretching on forever in every direction you could choose to look. You are embedded in something that, as far as physics can tell, simply does not stop. Not in time, going forward. Until the universe cools and darkens, and entropy reaches its maximum. Not in space, in any direction you might choose to travel. Not in the deep structure of the quantum vacuum, which seethes with activity at every point in the cosmos equally, from here to whatever there is no edge of. The universe, as best we can tell, doesn't end. It just continues, and continues, and continues, in every direction, at every scale, at every level of description we have so far reached. That's the answer. Not a comfortable one. Not a final one. But the most honest one physics can currently give. And the next time you look at a star, remember that the light reaching your eyes left that star years or centuries or millennia ago and has been traveling through space that has no known edge. Space that simply is, in all directions, without limit. That's the universe you live in. That's the space you're floating through right now. Vast beyond any concept of vastness you came here with. Old beyond any intuition of age. And as far as anyone can tell, without end. Good night.